Question 1. A stone is falling at a constant velocity vertically down a tube filled with oil. Which of the following statements about the energy changes of the stone during its motion are correct? Let's think about this stone. It's falling with a constant velocity downwards, and that's due to the weight of the stone. There's a force, an equal and opposite force of drag acting back up the way. Because it is falling down, it will be losing potential energy. If it's going at a constant velocity, it will have kinetic energy, and it will also be gaining some thermal energy. Because of the friction, it'll be gaining thermal energy. So which of the statements are true? The gain in kinetic energy is less than the loss in gravitational potential energy. Well, kinetic energy is constant. The gain in kinetic energy is 0. So kinetic energy gain is 0, but it is losing gravitational potential energy. So this is true. Number 2, the sum of kinetic and gravitational potential energy of the stone is constant. This would only be true if there was no frictional forces. If we go back to the law of conservation of energy, the total energy of a system is conserved assuming no external forces apply. Well, friction's applying here, and some of that energy will be lost to heat, so that's not true. Number 3, the work done by the force of gravity has the same magnitude as the work done by friction. Okay, the work done by the force of gravity is force times distance, and the work done by the force of friction is force times distance. The forces are the same because it's travelling at a constant speed. So the forces are the same. The distance travelled due to the work done by these forces is the same because it's travelling at a constant velocity. So yes, this is true. The answer is B. Question 2. A company designs a spring system for loading ice blocks onto a truck. The ice block is placed in a holder H in front of the spring, and an electric motor compresses the spring by pushing H to the left. So this will be elastic energy in here. When the spring is released, the ice block is accelerated towards the ramp ABC. When the spring is fully decompressed, the ice block loses contact with the spring at A. The mass of the ice block is 55 kilograms. Assume the surface of the ramp is frictionless, so that means it's a constant speed. And it'll have kinetic energy, and that the masses of the springs and the holder are negligible compared to the mass of the block. So what will happen is the block will travel at a constant speed across here, and then it will travel up this ramp. The block arrives at C with a speed of 0.9 meters per second. Show that the elastic energy stored in the spring is 670 joules. Well, elastic energy has the equation half kx squared. But we don't know any of those things. We don't know the extension of the spring. We don't know the spring constant. So we have to think of another way of doing it. Aha! Wait a minute. We know that all the elastic energy turns into kinetic energy and gravitational potential energy. And up here, it will have kinetic energy because it'll still be moving, and we can see that it's still moving here, and potential energy. So if we can work out what the sum of kinetic energy and potential energy is at C, then we can work out what the elastic energy is. And we can do that. So a half times the mass of the block, which is 55, times the speed, which is 0.9 squared, plus 55 times 9.81 times the height, which is 1.2, gives us a value of 669.7 joules, which is, of course, given to two significant figures because the rest of the data is given to two significant figures. That's A1. A2, calculate the speed of the block at A. At A, this point here, there is no potential energy. So all of the elastic energy is transferred to kinetic energy at that point. So we have 670 equals a half mv squared V is equal to the square root of 2 times 670 divided by the mass, which is 55. And if we work that through, that's 4.9 meters per second. Question 3. A student of weight 600 newtons climbs a vertical ladder 6 meters tall in a time of 8 seconds. What is the power developed by the student against gravity? So the student is doing work against gravity, and the power is equal to work done over time. But we know that work done is equal to energy transferred. So therefore power is energy transferred over time. But what is the transfer of energy here? Well, he's gaining potential energy. So actually the equation for power here is mgh, which is potential energy, over time. Which is, mg is the weight, so that's 600 newtons, times the height, which is 6, divided by 8, so that's 3,600 divided by 8, which will give us 450 watts. The answer is D. Question 4. The diagram below shows part of a downhill ski course which starts at point A, 50 metres above the level ground. Point B is 20 metres above the level ground. So that means that A to B is, basic maths, 30 metres. A skier of mass 65 kilograms starts from rest at point A, and during the ski course, some of the gravitational potential energy is transferred to kinetic energy. From A to B, 24% of the gravitational potential energy transferred to kinetic energy. Show that velocity at B is 12 meters per second. Okay, so the loss of potential energy from A to B is equal to EP equals mg, the change in height, which is 65 times 9.81 times the loss of height, which is 30. That means that it is losing 19,129.5 joules of potential energy. Now 24% of that is transferred to kinetic energy. So the kinetic energy at B is equal to 24% of 19,129.5, which gives us a value of 4591.08 joules. That's how much kinetic energy it's got at B. We want to use that value to find out what the speed of the object at B is. I know I'm using too many decimal places and significant figures. I just want to stay accurate until we get the final answer. So V equals the square root of 2 times 4591.08 divided by 65, which gives us a value of 11.9 meters per second. Of course, everything is to two significant figures, so the answer is 12 meters per second, which is what it said in the question. Fabulous. Question 5. A motor of input power 160 watts raises a mass of 8 kilograms vertically at a constant speed of 0.5 meters per second. What is the efficiency of the system? I'm going to give you an exam tip. When you're thinking of power, I know you often think of the idea of work done over time or energy transferred over time. Why am I writing this out? It's taking ages. But actually, sometimes when you're looking at a mechanical system or something that's moving, a very quick formula for power, which is useful, is force times velocity. Pop that in the memory bank. Okay? So when we're looking at efficiency, we're looking at the useful output power over the total input power. Useful output power. Right, well that's the power that your man's using, right? So it's force. So it is 8 times 10. That's the force, because that's his weight. Times the velocity, 0.5. And the total input power is 160. You'll notice I've used 10 there, by the way, for gravity. If we're doing multiple choice questions, it's not worth getting into small details like 9.8. That's my view anyway. Because we're looking at 80 times, so it's 40 divided by 160. So our efficiency is 25%. Exam tip is power equals force times velocity. It's a very useful formula to remember. Question 6. An object falls from rest from a height of h close to the surface of the moon. The moon has no atmosphere, just like a physics Christmas party. When the object has fallen to a height of h over 4 above the surface, what is the ratio of kinetic energy of the object h over 4 over gravitational potential energy of the object h? My goodness, what a mouthful. Okay, well we can do this one easily. The bottom denominator is just mgh, or let's just call it EP. So the key for us is to work out what the kinetic energy of the object is at h over 4. Well, we know that EP at the start will equal to EP at h over 4 plus EK at h over 4. And EP at h over 4 is equal to EP over 4 plus EK. So EK is equal to EP minus EP over 4. So EK is equal to 3/4 EP. Now if we pop that up here, and the ratio then is 3/4 EP over EP, these two cancel, the ratio is 3/4 A. The tension in a horizontal spring is directly proportional to the extension of the spring. What that's basically saying is this relationship holds true. The energy stored in the spring at extension x is E. What is the work done by the spring when its extension changes from x to x over 4? Now, here's my exam tip. Whenever you see the word work done and we're looking at energy, I always write down work done equals energy transferred. It is a super useful thing to have in your brain to remind you how to do these things. We know what the elastic energy is at x, but what is the elastic energy at x over 4? Well, it's half k x over 4 all squared, which is a half k x squared over 16, which is basically E over 16. So the energy transferred between x and x4 is E minus E over 16. So it's 15E over 16. That's the energy transferred going from x to x over 4, which is equal to the work done. So the answer is D. Question 8. A ball is thrown vertically upwards. Air resistance is negligible. What is the variation with time of the kinetic energy of the ball? Let's think about this ball. It's going to be very fast to begin with. So kinetic energy is going to be maximum at t equals 0. That rules out this one. It's eventually going to get to the point at the top of the trajectory where EK equals 0. So in the middle, we're looking for EK to be 0. That's correct. That's correct, and that's correct. Kinetic energy is a scalar. That means we're not really interested in direction, and it can't be a negative. So that rules out A. So we're looking at B or D. There's no linear function to this. I can't see this B being correct because there's nothing linear about kinetic energy. It's got V squared in it. It's a parabola. I don't see it. So I'm saying it's not B. I'm saying it's D. Question 9. Before I start question 9, I know what you were thinking when you tried this. You were thinking, ugh, it's impulse. And there's lots of momentum. Why is Sally making me do this? Well, you will note that IB Physics all links together. The ultimate exam will be a linking of concepts. That's the whole point of the new syllabus. You have to start doing problems of topics that you have done before. And eventually this will work into the work done on the ball. So let's go with this. Let's put all our effort into it and see how much you remember from A2. Question 9. The graph shows the variation with time of the horizontal force exerted on a tennis ball by a racket. And we can see this graph here, a force time graph. You'll be alerted from A2 to remember that the area under a force time graph is equal to impulse. A tennis ball was stationary at the instant when it was hit. The mass of the tennis ball is this. So let's write some stuff down. The area under the curve, so we know that impulse's area under the curve is 0.84 newtons a second. If we didn't remember that area under the curve is equal to impulse, then the units of this would give you a clue. Calculate the speed of the ball as it leaves the racket. So A. J, which is the impulse, equals the change in momentum, which is mv minus mu, which is mv minus u. Now u is 0, so J is equal to mv. V equals J over m, so 0.84 divided by 5.8 times 10 to the minus 2 gives us a value of 14.5 meters per second. That's A. B. Show that the average force exerted on the ball by the racket is about 50 newtons. Again, the word average force tells me it's impulse. That's a little exam trick from A2. Average force times time equals impulse. The average force here we want to find out, so it's impulse divided by time. Impulse is 0.84. What's the time? The time over which this ball was in contact with the racket. You can see it starts at 12 milliseconds and ends at 28 milliseconds. That means it's in contact with the racket for 16 milliseconds. So 0.84 divided by 16 milliseconds is 52.5 newtons, which is around about 50 newtons, which is what the question asked. Perfect. B. Determine with reference to the work done by the average force the horizontal distance travelled by the ball while it was in contact with the racket. Okay, I'm going to write C up here. I've seen the word work done, so I'm just going to write down this just to see if it helps. Work done equals energy transferred. Right, we know work done is equal to average force, in this case, times distance. We know what the average force is, we don't know what the distance is, but what we can do is work out the energy transfer, because this ball has ultimately gained kinetic energy, hasn't it? It's transferred into kinetic energy. So D is equal to half mv squared over the average force. We know a half times the mass of the ball. I'm writing very small, I'm so sorry. Times 14.5 squared divided by the average force, which is 52.5, gives us a distance of 0.119 meters. We'll put that to 2 decimal places, 0.12 meters. Okay, again, you've found this idea of work done equals energy transferred as a real helping point or a starting point when you're dealing with work done questions. Question 10. A net force F acts on an object of mass m that is initially at rest. The object moves in a straight line. The variation of F with distance is shown. Okay, exam tip alert. Whenever you see a force distance graph, you write the words area equals work done underneath it. Like that. What is the speed of the object at distance S1? So what's the speed here? At this point it's got kinetic energy, and we know that work done is equal to energy transferred. It's gained kinetic energy from 0. That means the area is equal to the kinetic energy. And we can work out the area just using algebra because it's a triangle. And the area of a triangle is a half base times height. So the area of this triangle is half S1 F1. And it's equal to kinetic energy, which is a half mv squared. So we can get rid of those halves because there's a half on each side. And we can rearrange for V. V squared is equal to S1 F1 over m. So V is equal to the square root of S1 F1 over m, and that relates to B. Question 11. A cyclist rides up a hill of vertical height of 100 metres in 500 seconds at constant speed. The combined mass of the cyclist and the bicycle is 80 kilograms. The power developed by the cyclist is 200 watts. So that's the power in. What is the efficiency of the energy transfer in the system? So the efficiency is the power out, or the useful power out, divided by the total power in. And I think we'll use that little equation that I told you about earlier. Power is equal to FV over 200. And the force is the weight of this guy, so it's 800 times the speed, which is 100 over 500, divided by 200. 160 divided by 200, that gives us a value of 80%. Question 12. It's another one of these questions that involves material from previous topics, but we can't get away from that, all right? A ball of mass 0.25 kilograms is released from rest at a time t equals 0 from a height h above a horizontal floor. The graph shows the variation with time t of the velocity v of the ball. Air resistance is negligible. Take g to equal 9.8 meters per second squared. The ball reaches the floor after 1 second. Determine h. So you want to find out what the height of this ball is when it drops. I can see two immediate methods here. My first method is to recognise that the area under a velocity time graph is equal to displacement. So if I can find the area of this triangle, I can find the height of the ball. Why am I specifically using this triangle? Well, I know that the ball reaches the floor after 1 second. So the area under the graph until 1 second is the area that I'm interested in. And the area of this graph is a half base times height. So it's a half times 1 times 10. So the answer is 5 meters. That's it, 5 meters. If that seems too easy for you, let's use the SUVAT equations, S-U-V-A-T. We want to find out what S is. We know that U is 0. V, the final speed, is 10. We can see that there. A is 9.8. And you'll notice I haven't done minus 10 or minus 9.8 because I've chosen positive to be downwards, but if you put minus in there, it'll work too. And t is equal to 1. So we can use any SUVAT equation. Let's go with the easiest. S equals ut plus a half at squared. U is 0. S equals a half times 9.8 times 1 squared, which gives us 4.9 meters. You'll notice that this answer here, 4.9 meters, is different to 5 meters, but the examiner will give you either of those correct as long as you've shown your working. B1. Label the time and velocity graph using the letter M, the point where the ball reaches a maximum rebound height. So maximum rebound height means it's bounced on the floor and it's got back up to its point where it's maximum height. First thing I would say about that, at this stage, V will be equal to 0. So we know it's either this point here or this point here. Or, sorry, this point at the start. All right, so we know that this point here is where it's just hit the ground. And within that 0.1 of a second, it changes direction and starts to travel upwards again in the opposite direction with velocity. So this point here, where it hits 0, must be the maximum rebound height. Draw on the axis a graph to show the variation with time of the height of the ball from the instant it rebounds from the floor until the instant it reaches maximum rebound height. Okay, if it rebounds from the floor, it's going to start at 0. Maximum height is going to be here. Let's just say max height there. And we want to know what shape to make it. We know that it will gain height very quickly. And then as the velocity of the ball starts to slow, the height of the ball will start to slow at the same rate. So what we'll find is the graph looks like this. And I've just missed my max point. Let's make it a bit bigger. Like that. On to C. Estimate the loss in mechanical energy of the ball as a result of the collision with this floor. What does that mean? Okay, so it's collides with the floor here, and it's got a certain amount of energy there. And then after collision with the floor, it's got energy here, so E1 and E2. It's got kinetic energy at both points, but the kinetic energy is different. So if we can find out the kinetic energy at point 1, and then the kinetic energy at point 2, and find the difference in those two, we'll find the loss in mechanical energy. I'm now trying to remember all of the values. What was the mass of this object? It was 0.25 times, and it had 10 meters per second before it hit the ground. After it hit the ground, it's got 5. So half times 0.25 times 5 squared, which gives us a value of 9.4 joules. That's the loss in mechanical energy of the ball as a result of the collision with the floor. Determine the average force exerted on the floor by the ball. Average force, I'm thinking of impulse. Ft equals mv minus mu. So F is equal to mv minus mu over t. So 0.25. V is the final speed, so that's 5, minus the initial speed, which is minus 10, over t, and the time in contact with the wall was 0.1 seconds. Let me show you to prove. 0.1 seconds. So the answer there is, if I pop it all into the calculator, 37.5 newtons. And D2, suggest why the momentum of the ball... Have I missed a question? Oh yeah, I have, look. B2, state the acceleration of the ball at maximum rebound height. State means the answer's in the question. It's either in the graph or it's in the question. Okay? State the acceleration of the ball at maximum rebound height. Well, anything in free fall, anything that's a projectile, anything that's flying about in the Earth's surface has the same acceleration at all times. The acceleration of the ball is the force due to gravity. And in this question it says it's 9.80 meters per second. Sorry, I missed that. Now we can do D2. Suggest why the momentum of the ball was not conserved during the collision with the floor. So what the ball does is that it collides with the floor. And so it goes down like this and then collides back up again. And it changes in momentum. But what the floor does, it's part of the system, is it recoils slightly. Maybe shakes a little bit. And that shaking of the floor has momentum as well. So this question says, suggest why the momentum of the ball was not conserved. Well, one, the momentum of the system of the ball and floor system was conserved. Some of the ball's energy, some of the ball's momentum was transferred to the floor. Now, I made a big mistake there. I said some of the ball's energy was transferred, and actually I made that mistake because a lot of students make that mistake. When you're talking about the law of conservation of energy and the law of conservation of momentum, they are two very clear and distinct concepts. Make sure you don't make the mistake that I just made. Okay? Question 13. What is equivalent to the ratio of specific energy of a fuel over energy density of a fuel? And remember, in mass of the majority, step 1 of this topic, we talked very clearly about the difference between those two. The specific energy of a fuel is the energy released per unit mass. The energy of a fuel is the energy released per unit volume. So if we're looking at the ratio there, the joules can cancel out. And actually we can do this, can't we? Well, that's a unit of volume. That's a unit of mass, which is effectively volume over mass. Oh, which is equal to 1 over density. So the answer is B. Question 14. The Sankey diagram shows the energy transfers in a nuclear power station. Electrical power output of the power station is 1,000 megawatts. What is the thermal power loss in the heat exchanger? So what's this? Well, the electrical energy output is 1,000 megawatts, and that is the equivalent of 4 squares. And look, the thermal energy loss in the heat exchanger is 4 squares as well, so that must also be 1,000 megawatts. The thermal loss in the turbine is 2 squares, so that's 500 megawatts. So our answer is 1,000. And just to be for completeness, our total input is all these added together, which is 2,500 megawatts. This is where I leave you. And as a reminder, I am leaving you because eventually you have to start working on these past paper problems yourself. I've given you some really good exam tips here. We've talked about the areas under graph and how to spot what they mean. We've talked about this concept of work done equals energy transferred. And I've talked you through a number of different types of energy, power and efficiency questions. I've left you with some easy ones after me and then 2 little difficult ones at the end. They're not physics difficult, they're maths difficult. So just relax and try and do them yourself. And I will see you in step 3 of the Tribe Success Path, which is propel your progress. Let's go. Bye.